working across from a lot of materials department with my mentor Ryan on characterizing 35 semiconductor thermoelectrics. So, a lot of you saw this graphic earlier today. It's the energy flow in the U.S. in 1 year, in 2008. And on the left here, we can see all our sources, and the widths of these lines correspond to the quantity of the energy that's coming from these. And you can see what it's like converted into, where it's allocated. And then you can see that we're wasting over half the energy that we generate. And all that energy just gets released as waste heat. So fortunately, there are materials that can convert this waste heat into usable electricity, and they're called thermoelectrics. And what's good about them is that they're solid state, no moving parts, very low maintenance. Gives them applications in really hard to reach places like under cars or in space. The Mars rover actually has one that uses the temperature difference between space and its interior to power some of its systems. Now, what rates the thermoelectric's performance is something called the figure of merit, and it depends on three of the material's properties. It's electrical conductivity, it's thermal conductivity, and the Seebeck coefficient, which is the relationship between the temperature difference and the voltage that it drives. So obviously, if we wanted to maximize this figure of merit, we want a material with a high Seebeck coefficient and a high electrical conductivity and a low thermal conductivity. But unfortunately, those two values in the numerator, which we call the power factor together, are related to the carrier concentration in opposite ways. So as you, this thing work? Yes. As you increase your carrier concentration, you can see that the Seebeck coefficient decreases and the conductivity increases. So there's a certain balance in every material that you can find. At a certain carrier concentration, you're going to have a peak in your power factor and also a peak in your figure of merit. Now, semiconductors turn out to be really good thermoelectrics, and this can be explained in terms of energy states. So in an atom, each electron has a discrete energy level, and when you bring a lot of atoms together, these energy levels start to offset from each other, and they create energy bands. You have a valence band and a conduction band, and when you're down in the valence band, you're not conducting, and when you're excited up into the conduction band, you are conducting. And the distance between those two bands is called the band gap. In metals, these two bands overlap. So that's why metals are always conductive. And if we go back to that trend that we noticed, these basically have a really high carrier concentration, so they're going to have a high conductivity and a low Seebeck coefficient. On the other hand, insulators have a very wide band gap, which means they have a low carrier concentration and a high Seebeck coefficient. These aren't ideal when we're trying to maximize that power factor. Now, semiconductors lie in the middle of these two. They have a Seebeck coefficient and a conductivity in the middle, and we can actually tune the carrier concentration by doping these materials. We're adding impurities to change the carrier concentration, and that can help us find that optimal carrier concentration to maximize that power factor or that figure of merit. So when I say semiconductors, most people think about the elements of the group 4, silicon, what you'll find in your motherboards and everything, but turns out in thermoelectrics, it's actually beneficial to have more than one size of atom in your crystal structure. So if you're looking at your group 4s, you have one size of atom. It turns out you can make semiconductors by alloying group 3 and group 5 elements. So here's a indium phosphide, just a general 3-5 crystal structure. And what happens when you have more than one size of atom is you get a phenomenon called phonon scattering. And phonons can be seen as particles that carry heat. And because of the particle wave duality, it's easier to see them as waves that have different wavelengths. So each different size of atom is actually going to scatter a different wavelength of phonon. So the more different size of atoms you have in your lattice, the more you're going to scatter phonons, and you're going to drive that thermal conductivity down. You're not letting as many phonons pass through. So the system that we're studying is indium arsenide phosphide. It's a combination of one group 3 and two group 5 elements. And we grow it on top of an indium phosphide substrate. So in this case, we have 3 different sizes of atoms. We're scattering 3 different wavelengths of phonons. So we're really driving that thermal conductivity down. Now the way we grow it is through a process called a chemical beam epitaxy. Now, Ashley talked before about what molecular beam epitaxy was. This is slightly different in that we primarily don't use solids. We use liquid or gas sources. And the advantage to this is we can actually change out our sources without having to compromise the ultra-high vacuum that we keep in the chamber. At the same time, we're able to alloy group 5 elements, and you can't do that in molecular beam epitaxy because, say if you want to use phosphorus, and you really don't want to heat solid phosphorus, it's highly explosive. So we use phosphine gas instead, which is mustard gas, but that's okay. And we also have a faster growth rate with chemical beam epitaxy. Now, after we grow our material, we characterize them, and one of the measurements we do is called the Seebeck measurement. We basically measure a voltage that is driven by the temperature difference. So we use a multimeter to measure the voltage, and we use the thermocouples to measure the temperature difference that's driving that voltage, and we get that. And then we do a simple 4-point measurement to find the conductivity of our material. And then we do something called a Hall measurement to find our carrier density. Now, we all know from high school physics that a charged particle moving in a magnetic field has a force exerted on it. So with an electron, by the left-hand rule, if you have a particle moving, magnetic field perpendicular to it, it goes in the cross-product direction. Anyway, we have a square sample, and we have a current going across one diagonal. So these charges moving across that diagonal get a force exerted on them, and they get to the other diagonal, one of the corners of the other diagonal. So if we measure the voltage across that other diagonal, we get our Hall voltage, which basically tells us how many carriers we have per unit area, and it's called the sheet density. And when we have those two values, and the elementary charge is a constant, we can gain information about the carrier mobility, which is also good information to have when you're looking at electronic transport. So going back to this trend, we're trying to find that peak, that optimal carrier concentration that can give us that peak in power factor. And the first system that we studied was just silicon-doped indium phosphide. So this is the first part of the spectrum of indium arsenide phosphide without any arsenide. And what we did was dope it with silicon, and it's called conventionally doped because silicon is a pretty common dopant. And we see that we can reproduce that trend in the Seebeck coefficient. You see the Seebeck coefficient goes down as you increase carrier concentration, and your power factor reaches that peak and then goes down. So we found our peak to be a little over 10 to the 17 carriers. And then we studied unintentionally doped, which we call UID, and that's without any dopant. It's just things inside our growth chamber may have incorporated into the material and donated charge carriers. And this was an indium arsenide phosphide lattice, and we noticed that the Seebeck coefficient does follow that trend, say for that anomalous point there, and we think that might be because we got these weird indium droplets on our surface. And then we see that our power factor is rising, but we still haven't quite reached that peak yet. So as you can see, this project is still in its early stages. We want to study the entire spectrum, all the way from indium arsenide X phosphide 1 minus X, and go X equals 0 all the way to X equals 1. So that's indium phosphide all the way to indium arsenide. And we've done silicon doped, we've done unintentionally doped indium arsenide phosphide. We want to get everything in between here before we start doping with a rare earth to see how that compares, see if that's actually feasible. And we're doping with rare earths because they have a chance of either incorporating into the material in low concentrations and they'll provide charge carriers, or they can precipitate out of your material and give you nanoparticles, and those are another site for phonons to crash into, another wavelength of phonon you can scatter, and you're really driving down that thermal conductivity. So once that happens, we can explore other rare earths to see if that actually makes a difference. So we might try a line from them, and we can compare it to our conventionally doped and unintentionally doped samples. So I'd like to end my talk with some acknowledgments. I'd like to thank the Center for Science and Engineering Partnerships for funding this internship, the entire Palmstrom group for being really helpful, and my mentor Ryan Need for guiding me throughout this summer. And I can open up to questions.